Hello friends, welcome back to the video lecture. Today we will see the next type of titration for SYBSc Analytical Chemistry. We are dealing with the volumetric analysis. We have seen the two titrations, that is titration between strong acid and strong base, and the second one was titration between weak acid and strong base. Today we have to going to see the third type of titration, and it is nothing but the titration of strong acid and weak base. In short, it is known as SAWB, strong acid weak base. So in this titration we have taken the strong acid, hydrochloric acid, which is of 0.1 normality. Okay, and this hydrochloric acid is taken in burette. Weak base taken is 0.1 normal ammonium hydroxide, that is NH4OH, and it is taken in conical flask with the help of pipette. Now, as HCl is a strong electrolyte, so that's why it is taken as a titrant and it is taken in burette. Whereas NH4OH, that is ammonium hydroxide, is a weak electrolyte and it is taken in a conical flask, and hence it is considered as a titer. Now the nature of the graph of this titration is shown here. I have drawn the picture or the graph in which there is pH is taken on y-axis and volume of hydrochloric acid that we are adding from the burette is taken on x-axis. Okay, so this is the main part of the curve. This is the nature of the curve for this titration, and the vertical part of the titration curve lies from 3 to 8 pH units. It is lying between 3 to 8 pH units. Okay, so at the equivalence point is near to 25 ml of 0.1 normal HCl added, and at the equivalence point we get a straight line in this curve. Okay, and the straight line area is comprising from 3 to 8 pH units. Now we have to consider here the choice of indicator. Now we know that in this area of 3 to 8 pH units there are mainly 4 indicators have their transition range, and these are: first one is methyl orange. Methyl orange is having its transition range from 3.1 to 4.4. 3.1 to 4.4 methyl orange is there. Then methyl red is there, methyl red, and it is from 4.6 to 4.2 to 5.3. Sorry, 4.2 to 6.2, and the third one is bromothiamol blue. Bromothiamol blue is having its transition range from 6 to 7.6, and the last one is phenolphthalein indicator. It is having its transition range in the pH units from 8 to 10, near about 8 to 10. Okay, so these are all 4 indicators are suitable indicators for this titration, but at 25 ml near the equivalence point, our equivalence point is exactly equivalence point is 5.27. so that's why our the best indicator for this titration is methyl red, because this indicator is having its transition range exactly at the equivalence point of the titration. Okay, so that's why methyl red is acting as or can be considered as a best indicator for this titration. Okay, this is important because we have seen the 3 different types of acid base titrations, and in all these 3 the best indicator is different for all. Okay, so for strong acid strong base the best indicator was bromothiamol blue. For second one was weak acid strong base. In that case the phenolphthalein indicator was the best indicator, and in this case for the SAWB the methyl red is the best indicator. Okay, now we have to, now in the next point in this topic is we have to calculate the pH of the solutions at the different stages of the titration. Okay, now as there are many calculations are given in your text, but only 4 are essential, and these are at the start of titration what is the pH, then after adding some amount of titrant from the burette what will be the pH. Okay, we have taken here 10 ml of titrant added, then at the equivalence point what will be the pH of the solution, and after equivalence point when you are adding 1 or 2 ml extra titrant to the conical flask or to the titer, then what will be the pH of the solution. Okay, so why we are calculating this? These pH values we are calculating here, our attempt is to obtain the nature of the curve, nature of the graph for this type of titration. Okay, so first one is the pH of the solution at the start of the reaction. So at the start of reaction, friends, we have only ammonium hydroxide in the conical flask. In the conical flask we have only ammonium hydroxide, that is NH4OH solution. We doesn't added any solution of HCl. Okay, there is no HCl added, so obviously the pH will be towards the, as it is a weak base, so pH will be towards the basic side, and this graph indicating that when we are adding 0 ml of HCl added, so at the start of this titration the pH is towards the basic or alkaline side. Okay, and it is about near to 11 to 12. Okay, it is between 11 to 12. So we have to calculate here pH of the solution at the start of titration. Okay, so at the start of titration we have only ammonium hydroxide in the conical flask. As ammonium hydroxide is a weak base, it dissociates partially as NH4OH. It dissociates partially, so dissociation will be NH4 plus OH minus, NH4 plus OH minus. Okay, so what is the concentration of NH4OH? 0.1 normal. Okay, so as it is a weak base, so it dissociates partially, partial dissociation will take place. So let us take only X mole of this NH4OH will dissociate. Okay, so how many moles of that NH4 plus and OH minus will be formed? X moles. It will form X moles. These are the concentration at equilibrium. These are the concentration at equilibrium. When equilibrium is established, this is the concentration of these species. Okay, now the Kb value, that is base dissociation constant for this NH4OH, is constant value. This is the constant value at 25 degrees Celsius, and the value is 1.75 into 10 raised to minus 5. 1.75 into 10 raised to minus 5. Now the concentration of this Kb value can be calculated as concentration of, from the formula, concentration of NH4 plus into concentration of OH minus divided by the concentration of undissociated species, and undissociated species is NH4OH. Now I am putting the values. Concentration of NH4 plus at equilibrium is X into concentration of OH minus is again X divided by concentration of NH4OH is 0.1 minus X. Now again I am saying that, I am telling that I have already told you that this value of X is very small, because it is a weak base. It dissociates very less in or it ionizes in very less amount, so that's why X is very small. So that's so 0.1 minus X will be approximately equal to 0.1, and hence my equation becomes X into X, X square, and 0.1 minus X, it is approximately equal to 0.1. So Kb is equal to this. So therefore X square is equal to multiplication, cross multiplication will be there, Kb into 0.1. Okay, so what is the Kb? This is the constant figure, and it is given in the literature. So 1.75 into 10 raised to minus 5 into 0.1, that is 10 raised to minus 1. 0.1 is nothing but 10 raised to minus 1. So my x square value become 1.75 into 10 raised to minus 6. Multiplication of this x square is equal to this. So therefore take the square root of both sides. I get the value of x. So x is equal to, what is x? That is the concentration of OH minus. Concentration of OH minus is equal to x, and the square root of this is 1.313 into 10 raised to minus 3 molar. 1.313 into 10 raised to minus 3 molar. You can calculate using calculator or calci. Okay, as this is OH minus ion concentration, so therefore POH is equal to log of 1 upon OH minus ion concentration. We know that the formula, and hence POH will be 2.88. POH value of this, from this calculation we can get 2.88, and therefore pH will be 14 minus 2.88. 14 minus 2.88, and it is 11.12. It is 11.12. So this is the pH of the solution. This is the pH of the solution at the start of reaction or at the start of titration. Okay, very simple is there. Nature of the graph. What we have taken first. What is the titration? Nature of the graph. Then choice of the indicator. Then first calculation for the pH at the start of titration. Okay, in this way we can put the our calculation. Okay, so this is first calculation. Now the second calculation. Second calculation is for when we are adding 10 ml of SCl. When we are adding 10 ml of SCl from the burette to the conical flask, and in our conical flask we have already taken ammonium hydroxide solution. The pH of solution when 10 ml of 0.1 normal SCl added to 25 ml of 0.1 normal NH4OH. Okay, so this is the situation. We have in conical flask ammonium hydroxide NH4OH solution 25 ml, and in that solution we have added 10 ml of SCl. 10 ml of SCl is get added from the burette itself. Okay, so there is a reaction between SCl and NH4OH take place. As there is only a 10 ml SCl, this 10 ml SCl acid reacts with 10 ml of NH4OH, and only the neutralization reaction between this SCl and NH4OH of 10 ml will take place. Okay, so that's why out of 25, 10 ml of NH4OH will neutralize, and remaining NH4OH will be 25 minus 10 is equal to 15 ml. 15 ml of NH4OH ammonium hydroxide will remain unreacted. Okay, so very simple. But as we are adding SCl solution from the burette, the volume of the solution in the conical flask is increasing, and due to this increase in volume, the concentration of NH4OH will changing. Okay, so new volume in conical flask is equal to 25 already there NH4OH, plus we have added 10 ml of SCl, so it will become 35 ml. This is the new volume, and due to this change in volume, there is a change in concentration also, because concentration and volume are inversely proportional to each other. Okay, so that's why new concentration of this NH4OH will be calculated as old, and this is new. Old N1V1 is equivalent to N2V2. Okay, what is N1? It is 0.1. old concentration into what was the old volume, it is only 15 ml which is remain unreacted, is equal to N2 is what, that we have to calculate it, into V2 is what, a new volume, that is 35 ml. Hence N2 is equal to, do a cross multiplication, N2 is equal to 0.1 into 15, 1.5 divided by 35, and hence N2 is equal to, the ratio of this is equal to 0.04236. You can solve this ratio by using a calculator, 0.04286. Okay, so this new concentration is needed for the further calculation. Okay, now as we are adding NH4OH, we are adding HCl to the NH4OH solution, there is a neutralization reaction between them takes place, and it can be shown like this, NH4OH plus HCl, and as there is reaction between base and acid, there is a formation of salt, that is NH4Cl plus water. The salt and water will form. Okay, so what is the concentration? So what is the, how many moles of this will react? It will form 0.1 into 0.1 into 25, no, 0.1 into 10. Okay, 0.1 into 10. Why 10? Because 10 ml of NH4OH is reacting only with 10 ml of HCl. Okay, and this is a neutralization reaction between this acid and base. Okay, so again this is having 0.1 concentration and into 10 ml of this HCl that we are added. Okay, the reaction between these them two will be, it is forming 1 millimole of NH4Cl will be formed. Okay, 1 millimole of ammonium chloride will be formed here. Now the concentration of NH4Cl, that is salt, is equal to millimoles of salt form divided by total volume in ml. So what is the millimoles of salt? It is 1. And what is the total volume? Total volume is 35 ml. So 1 divided by 35, this is the concentration of salt NH4Cl. Okay, so 1 upon 35, the answer will be 0.02857. 0.02857. Okay, so this is the concentration of NH4Cl. Okay, now this is the stage at which we have added 10 ml of HCl from burette to the conical flask, in which we have taken the base, that is ammonium hydroxide. At every stage of this titration before the equivalence point, there are both salt and base. This NH4Cl salt and base both are present in the conical flask, and hence as a combination of these two, there is a formation of basic buffer. Okay, so a basic buffer will be formed. Basic buffer is nothing but a combination of a base and a salt, its salt with strong acid. So base is NH4OH and its salt with strong acid is HCl. Okay, so what is the salt? NH4 plus is the cation from the base. Okay, and Cl minus is the anion from the acid. So this is the combination of these two chemicals and it is forming a basic buffer, and hence we have to calculate the hydroxide ion concentration, that is OH minus ion concentration of this basic buffer. Okay, and it is nothing but OH minus ion concentration of this basic buffer can be calculated by using a formula KH into concentration of salt, KB into concentration of salt divided by concentration of base. Now what is KB? KB we know that 1.75 into 10 raised to minus 5 into concentration of salt is what? 0.2857 and divided by what is the concentration of base that we have calculated? Yes, N2. It is 0.4286. So when you solve this sum by using calculator, you will get the concentration of OH minus, and the answer of this concentration of OH minus is 2.625 into 10 raised to minus 5 molar. This is the concentration of OH minus. Okay, 2.625 into 10 raised to this is reverse concentration of base is at the numerator divided by concentration of salt. So these figures will get reverse. 0.4286 0.2857. Okay, and the answer will be OH minus and concentration is equal to 2.625 into 10 raised to minus 5 molar. Okay, so you will need a calculator at every stage of this calculation. Okay, keep in mind this formula. Now as we know the OH minus and concentration, we can calculate the POH value. So POH will be log of 1 upon OH minus and concentration. When you put this value OH minus and concentration in this figure, you will get the POH, and the POH in this case is 4.581. Okay, as this is POH, so you can calculate pH. pH is equal to 14 minus this, that is 4.581, and the pH will be approximately equal to 9.419. So this is the pH of the solution in the conical flask when we are adding 10 ml of the HCl from the burette. Okay, so this is the second calculation when we are adding 10 ml of the HCl to the 25 ml of ammonium hydroxide. Okay, now we have to calculate the third pH calculation, and it is nothing but the pH of the solution at equivalence point of the titration. pH of the solution at the equivalence point of the titration. So at equivalence point, what is the situation? At equivalence point, pH at equivalence point. At equivalence point, 25 ml of HCl that we are added from the burette to the 25 ml of ammonium hydroxide solution which is taken in conical flask. Okay, and there is a complete reaction, neutralization reaction between them takes place, and no any base or acid remain unreacted at this stage. Okay, so the total volume in this case, total volume will be 25 plus 25, both of acid and base will equal to 50 ml. It is equal to 50 ml. Okay, now as there is only salt and water present in this case, okay, and this salt the neutralization reaction between them forming salt and water can be shown like this: NH4OH plus NH4 HCl, it is forming NH4Cl plus water. Okay, concentration was 0.1 into 25 ml. Concentration was 0.1 into 25 ml. The reaction between them will form 2.5 molar of ammonium chloride, that is salt, will be formed. Okay. Now the concentration of NH4Cl can be calculated. Millimoles of salt formed divided by total volume in ml, and is equal to, millimoles are 2.5 and total volume is 50 ml. Okay, so 2.5 divided by 50, so I think 0.05. This is the concentration of NH4Cl at the equivalence point. Okay, 0.05. Now, as the salt is formed in the conical flask and our medium is aqueous medium, so we have to consider the hydrolysis of this salt. Hydrolysis means nothing but the reaction with water. So this NH4Cl, that is ammonium chloride, from which ammonium hydroxide ammonium ions are get hydrolyzed, okay, plus water, there is a formation of NH4OH plus OH minus. So what is the concentration of NH4 plus? 2.5. Sorry. So NH4 plus means ammonia. This is the concentration of salt, that is 0.05 minus Y. So what is Y? This is the original concentration of ammonium chloride salt which is formed after the neutralization reaction between this. Out of this concentration, Y amount of this salt will undergo hydrolysis. Okay, only a fraction of this will undergo hydrolysis. Okay, so it will form Y of ammonium hydroxide and Y of OH minus ion at equilibrium. Okay, so therefore in this case the concentration, these are the concentration at equilibrium stage. Now the KH, here KH, that is hydrolysis constant, is equal to Kb into concentration hydrolysis constant for this reaction can be calculated as concentration of NH4OH into concentration of OH minus divided by concentration of NH4 plus. Concentration of NH4OH is Y into OH minus Y divided by 0.05 minus Y. It is approximately equal to Y square divided by 0.05. This is the formula for KH. But this hydrolysis constant KH we can also calculate by a special formula. KH is equal to KW upon KB. Okay, and we know that KW is 1 into 10 raised to minus 14. This is the ionic product of water, and KB is 1.75 into 10 raised to minus 5. So what will be the ratio? What will be the answer? The ratio of these two is 5.714. 5.714 into 10 raised to minus 10. This is the value of KH. Now we have to put this value of KH into this equation. Now my equation becomes, KH is equal to 5.714 into 10 raised to minus 10 is equal to y square divided by 0.05. So therefore y square is equal to cross multiplication 5.714 into 10 raised to minus 10 into 0.05. Okay, and the multiplication of these two becomes 28.57 into 10 raised to minus 12. 28.57 into 10 raised to minus 12. So this is y square. So take a square root of both sides, you will get the value of y, and value of y is nothing but concentration of OH minus ion. Concentration of OH minus ion is equal to the square root of this is 5.345 into 10 raised to minus 6. 10 raised to minus 6. This is OH minus ion concentration. So therefore POH is equal to POH of this solution sorry. So this is H plus will be formed here. NH4 plus OH minus from this water will react with this NH4 plus. Indeed, there is a formation of NH4OH, and here H plus will be formed. Okay, here again H plus. Okay, Y is equal to concentration of H plus, and hence we directly get the pH of the solution. So pH of the solution is equal to log to the base 10 of log of 1 upon H plus ion concentration. So put the value of this H plus ion concentration in this equation, you will get the pH of the solution, and pH of the solution is 5.27, I think 5.27. Yes, this is the pH at the equivalence point of the titration. Okay, some lengthy process is there, you have to keep in mind stepwise. Okay, and the third calculation is the pH of the titration when 26 ml of titrant, that is SCl, is get added to the NH4OH solution. pH of the solution, pH of solution when 26 ml of 0.1 normal HCl added to 25 ml of 0.1 normal NH4OH. Now consider the situation here. What is the situation? This is the situation after equivalence point. Means 25 ml of ammonium hydroxide that we have taken in conical flask, it is already get neutralized by the 25 ml of HCl added from the burette, and hence we have added here 1 ml extra of HCl after equivalence point. So in our conical flask, whatever the ammonium hydroxide were there, it was totally neutralized, and only 1 ml of 0.1 normal HCl extra that were added from the burette is remaining unreacted. Okay, so in this case we have only H plus ion concentration in excess that we have to calculate. Okay, and it is calculated by a simple manner, that is H plus ion concentration is equal to millimoles of H plus form divided by total volume in ml, total volume in ml. So millimoles of H plus, how many millimoles of H plus will be formed? The concentration was 0.1 into 1 ml is only remaining unreacted, so 0.1 into 10 divided by total volume 26 plus 25, it will become 51. So 0.1 into 1, 0.1, divided by 51. So concentration of H plus will be here 0.00196 molar. Hence pH is equal to log to the base 10 of 1 upon H plus ion concentration. Put the value of this in this denominator, you will get the pH as 11.12. This is the pH of the solution. Sorry, the pH of the solution will be 2.708. So this is the pH of the solution at the end of titration, when we are adding 26 ml of HCl from the burette, 1 ml extra after equivalence point. Okay, so in this way the 4 calculations are there which are must for the exam point of view. Okay, and in this way we have completed here all the 3 main parts of or types of acid base titration. First one was strong acid strong base. In that case we have taken the example of HCl and NaOH. Then the second one was strong base and weak acid. So weak acid was taken acetic acid and base was taken NaOH. Okay, and this is the example of strong acid weak base. Example is HCl and NH4OH. Okay, so thank you for listening this video lecture. Thank you very much. Have a nice day.